In this video, I will show you how to find the resultant vector when two vectors are acting together, even when the direction of the vectors are not just north, south, east, or west. Now, the way my brain works, I like to have a system for everything, and this is no exception. So these notes will guide us as we find the resultant vector. I'm going to do this four-step process. I'm also going to use this little graphic organizer to keep our work organized. While playing golf, Anna hits a ball at a speed of 40 miles per hour in the direction of east, 35 degrees north. At the time, a 5 mile per hour wind is blowing due east. Find the resulting speed and direction of Anna's ball. So here's how this little chart is going to work. In this column, we're going to put one vector. So that's going to be the ball velocity on its own. The other vector that's happening is the wind. So in this column, we will record everything pertaining to the wind velocity. And in the final column, we will record the resultant vector, because these two vectors are acting together. Now, how about the rows? In the first row, we are going to record the magnitude and direction of each vector. So when I talk about r and theta, I'm talking about the magnitude and direction. And for the purposes of this chart, anytime I'm talking about the direction on this chart, I'm talking about the type of direction where we simply start at the positive x-axis and measure counterclockwise from the east. Okay, and in the last row, I'm going to record the component form of each vector, horizontal and vertical. So, this chart will fit very well with my system. So step one is to determine the magnitude and direction for each vector. Let's go ahead and do that now. Let's start with the ball velocity. It says Anna hits the ball with a speed of 40 miles per hour. So right there, that's the magnitude. So we can just go ahead and write that down, 40. In the direction of east, 35 degrees north. Okay, we need to convert that to theta measured from the positive x-axis. So we need to convert this direction over. So if I want to find the direction of east 35 degrees north, this means start at due east and then turn 35 degrees towards the north. So if I start at due east and I begin to turn 35 degrees towards the north, then my vector is going to end up in this position, where this angle right here is 35 degrees. Now, often we need to add or subtract from 180 or 270 or 90 or something like that. But this vector, this angle, is actually in the first quadrant. So this is the actual angle that we want. This angle is being measured from the positive x-axis. So we don't actually have to do any special conversion. 35 degrees is the angle that we want. So when we talk about r comma theta, for this particular problem, the direction theta is the 35 degrees. Now, how about the wind velocity? Okay, what did it say about the wind? The wind is blowing 5 miles per hour due east. So we need the magnitude and the direction. So the magnitude is simply the 5 miles per hour, and I should put units here. So miles per hour, 5 miles per hour. That's the magnitude. Now the direction is due east. So look, due east, let me just copy this for a second. All right, I'll use this compass rose to show what the wind is doing. If the wind is blowing due east, that is 0 degrees. Measured from the positive x-axis, it is the positive x-axis. So theta is simply 0 degrees here. All right, so I'll just record that, magnitude of 5. This direction is 0 degrees. So with that, we have completed step 1. We have determined the magnitude and direction for each vector. Step 2, convert the magnitude and direction to component form. Using this little formula, r cosine theta and r sine theta will give you the horizontal component and the vertical component. R cosine theta, r sine theta. Okay, and remember, this is r, this is theta. So if I do r cosine theta, I am talking about 40 cosine 35. If I do r sine theta, that is 40 sine 35. This will give me the component form. For the wind velocity, if I do r cosine theta, well, actually, let me stop. Let me not use this formula r cosine theta. That's not necessary when you're dealing with a direction that is either north, south, east, or west, a quadrantal angle, if you will. We don't need to do any r cosine theta, r sine theta. Instead, let's use our common sense. When we do component form x comma y, the x is the horizontal component and the y is the vertical component. But if you're talking about a vector that is due east, that is the horizontal component. It's all horizontal. So because it's to the east, that's going to be positive. So the horizontal component will simply be positive 5. There is no vertical component, so for the vertical component will be 0. So do not bother with r cosine theta, r sine theta when you have north, south, east, or west for the direction. So going back to the ball velocity, we have set up for the component form. Let's do the calculations. So 40 cosine 35, we will just write 40 cosine 35. Make sure your calculator is in degree mode. So that's 32.77 degrees. Well, not degrees. Miles per hour. And if we do 40 sine 35, that's 22.94 miles per hour. Okay, and we already have the wind velocity in component form because it was just due east. And this is all miles per hour. With that, we have completed step 2. We have converted the magnitude and direction to component form for both vectors. That brings us to step 3. We're going to add the vectors to find the resultant vector in component form. So all we need to do is add these vectors, and that will give us the resultant vector. So I'm just going to add 32.77 with 5. So that's going to give me 37.77. 0.77. And then, of course, I'm going to add 22.94 and 0, those vertical components. So that'll just be 22.94. So that's it for step 3. We have added the vectors, and now we have the resultant vector in component form. That just leaves step 4. We need to determine the magnitude and direction of the resultant vector. So we're just going to take this and find the magnitude and direction, all right, which we will put right here. So let's start with the magnitude. All right, for the magnitude, we're just going to use the magnitude formula. So that's going to be the square root of 37.77 squared plus 22.94 squared. All right, just calculate that. Boom. That is 44.19 miles per hour. Okay, so that is the speed of the ball, the resultant speed of the ball with the wind acting on it. So let's go ahead and write that down as the magnitude of the resultant vector, 44.19 miles per hour. Okay, that's the magnitude. Now we need to find the direction. Okay, let's find the direction. So we will find the direction in a similar way that we did for the individual vectors. Let's make a little diagram using our compass rose. So, okay, we've got the component form here. Notice how both of these are positive. That means we are going to the east and to the north. You know, we're going right and up on this diagram. So that's going to put us in the first quadrant. So let's go ahead and draw our vector into the first quadrant like this. Okay, now let's go ahead and make a little triangle out of it. All right, we've got this right triangle. This is the angle that we're trying to find. All right, that's going to be the direction measured from the positive x-axis. So let's see. So it was 37.77 to the east. So that's here, 37.77. And 22.94 north, that's the vertical component. So that will be here in the diagram, 22.94. So we can use tangent to calculate what this angle is, because the tangent of theta is going to equal 22.94 over 37.77. Therefore, the angle, the direction, will equal the inverse tangent of 22.94 over 37.77. Okay, so just go ahead and put that in your calculator. And bam. So that is 31.27 degrees. And we can go ahead and record that here on the chart, 31.27 degrees. So now we have the magnitude and the direction of the resultant vector. Now, there's only one more thing that we need to do. This is basically the answer, all right? We've got the magnitude, we've got the direction. There's just only one small thing. The directions are given to us in another form. We were given directions like east, 35 north. We were not given directions in this manner where we just have an angle measured counterclockwise from east. All right, we were given this yellow form of direction. So you have to write your direction in the same type of form that you're given in the original problem. So we need to convert this back to a direction that looks like this. So what am I going to do? What am I going to do? Let's see. Well, I don't have to actually do any additional calculations because I can picture this as being an angle that started at east. All right, so I could picture this as begin at east and then turn yourself. Hold on. For some reason I feel like doing this in green. Beginning at east, we would have to turn ourselves 31.27 degrees towards the north. And you would arrive at this vector. So we could describe this same angle as east, 31.27 degrees north. So that's all we have to do. So I'm just going to rewrite this whole thing. So we've got the magnitude and the direction, but the magnitude is 44.19 miles per hour. And now I will write the direction as east, 31.27 degrees north. So this is the final answer. Let's do one more example. Three forces with magnitudes 100 pounds, 40 pounds, and 89 pounds act on an object at angles 40 degrees, 150 degrees, and negative 50 degrees, respectively, with the positive x-axis. Find the direction and magnitude of the resultant of these forces. Well, in the last problem, we only had two vectors. This time we have three. So I'm going to have to modify my chart a little bit. So here I have expanded my chart to leave room for three forces and the resultant. And so in the first row, we're going to have magnitude and direction. And in the second row, we will have component form. So let's see. Magnitudes 100, 40, and 89. So the magnitudes are 100, 40, and 89. And these are pounds. Let's see. The directions are angles 40 degrees, 150 degrees, and negative 50 degrees, respectively, with the positive x-axis. So I can use these angles directly. I don't have to convert them to anything else, because when we do r comma theta and we write the directions on this chart, we want directions as measured from the positive x-axis. So this is perfect. So we have done step one of the four-step process. We have determined the magnitude and direction for each vector. Step two, convert the magnitude and direction to component form using the little formula r cosine theta, r sine theta. So r cosine theta, r sine theta. For force 1, that will be 100 cosine 40, and then 100 sine 40. So we can just find the value of these expressions using a calculator. So there you go. We're getting 76.60 and 64.28. Okay, and these are still pounds. Let's do the same thing for force 2. R cosine theta, R sine theta. So R cosine theta, that's 40 cosine 150. R sine theta, so that's 40 sine 150. Calculator. So this is what I'm getting. So first I have negative 34.64. And 20. Okay, how about force 3? Our cosine theta is 89 cosine negative 50. And our sine theta is 89 sine negative 50. Calculator. So here you go. We have 57.21 and we have negative 68.18. Okay, we have now completed step 2. We've converted the magnitude and direction to component form for all 3 vectors. Time for step 3. Let's add the vectors to find the resultant in component form. So I just need to add all 3 of these vectors. And when I add, I'm just going to add the corresponding components. So I'm going to add 76.60, negative 34.64, and 57.21. And that should give me the horizontal component of my resultant vector. I'm getting 99.17 pounds. For the vertical component, I will similarly add all of the vertical components. So 64.28 plus 20 plus negative 68.18. I'm getting 16.10 pounds. So we have now found the resultant vector in component form. That was step 3. Now it's time for step 4. Determine the magnitude and direction of the resultant. So I just need to look at this and find the magnitude and direction. Okay, so let's see. Magnitude. And direction. For the magnitude, we will just use the magnitude formula. So we will do 99.17 squared plus 16.10 squared and take the square root of all that. So that is 100.47 pounds. We can go ahead and record that on our chart of, this is the row for magnitude and direction. So we can go ahead and write 100.47 pounds. That's our magnitude. And now let's find that direction. When we do the direction, we should draw a little diagram. Looking at the component form, this vector is going to the right and up. So this is going to be a vector in the first quadrant. So go ahead and draw yourself a vector in the first quadrant. Then make a triangle out of it using the reference angle. I started to say reference angle, but because it's in the first quadrant, this is actually the angle that we want. This is the angle from the positive x-axis, so this is good. The horizontal component is 99.17, so it goes here. The vertical component is 16.10. So the tangent of the angle or direction should be 16.10 over 99.17. Therefore, the direction should be the inverse tangent of 16.10 over 99.17. Calculator. I'm getting 9.22 degrees. That's the direction. So let's go ahead and record that on our chart. 9.22 degrees. And that's it. That's the final answer, the magnitude and direction of the resultant vector. Let's put a box around it. All right, that's it. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video, and click over here to subscribe. That way you'll get every new video delivered right to your home screen.